Entonces, vamos a dar por iniciada esta defensa de tesis. Buenos días a todos. Hoy estamos reunidos porque esta es una tesis en la Universidad de Buenos Aires y la Universidad de Gante en Bélgica. Los directores fueron la doctora Adriana Patriarca, de la Universidad de Buenos Aires, y la doctora Sara de Sieger, de la Universidad de Gante de Bélgica. El jurado está compuesto por la doctora María Lidia Herrera, del Departamento de Química Orgánica de la Facultad de Ciencias Exactas y Naturales, es profesora asociada y además es investigadora principal de CONICET en el Instituto de Tecnología en Polímeros y Nanotecnología. La doctora Aurélie Crabbe, que es Assistant Professor del Departamento de Microbiología de la Facultad de Ciencias Farmacéuticas de la Universidad de Gante, Bélgica, y el doctor Marcelo Signorini del Departamento de Salud Pública y Veterinaria de la Facultad de Ciencias Veterinarias, Universidad Nacional del Litoral, y también investigador independiente de CONICET, Instituto Nacional de Tecnología Agropecuaria, Estación Experimental Agropecuaria Rafaela, y es además vicedirector del Instituto de Investigaciones de la Cadena Láctea INTA-CONICET. Voy a pasar al inglés, entonces, good morning to everyone. We are gathered today to assist to the presentation of the thesis of Maria Agustina Pavicich. It is a special event because this work has been directed by Dr. Andrea Patriarca from the Buenos Aires University and co-directed by Dr. Sara de Sieger from the Ghent University of Belgium. The jury is composed by Dr. Maria Lidia Herrera, Associate Professor at the Department of Organic Chemistry, Faculty of Exact and Natural Science, Universidad de Buenos Aires, and Principal Researcher at CONICET at the Institute of Polymer Technology and Nanotechnology. Dr. Aurélie Crabbe, Assistant Professor at the Microbiology Department, Faculty of Pharmaceutical Science at Ghent University, and Dr. Marcelo Signorini, Assistant Professor at the Department of Public Veterinary Health, Facultad Veterinaria de Ciencias Veterinarias, Universidad Nacional del Litoral, and Independent Researcher at CONICET at the National Institute of Agricultural Technology, INTA. So please, Agustina, the audience is all yours.
Thank you very much for the introduction, Alicia. And give me just 1 minute. So today I will be presenting my PhD thesis, which is entitled Investigation on the Fate of Alternaria and Alternaria Mycotoxins in the Apple Industry. And as said before, it was done jointly by the Faculty of Pharmaceutical Sciences of Ghent University and the Faculty of Exact and Natural Sciences from the Universidad de Buenos Aires, and jointly directed by Professor Andrea Patriarca and Professor Sara de Sieger. So to start, I will give you an overview of my presentation that will start with a brief introduction on the problem of Alternaria in apple. Then we will discuss the research objectives, and later we will go through the different chapters of the PhD to have some final conclusions. So to start, apple fruit is the third most popular fruit in the world, with 89 million tons harvested every year. In Argentina, in Patagonia, in the Alto Valle of Rio Negro province, apple fruit is one of the main crops of the area, with 538,000 tons harvested in 2019. Particularly, 65% of the varieties cultivated in the area correspond to red delicious variety, and 50% of the harvest gets destined for fresh commerce. 22% gets destined for export trade, and the remaining 28% gets destined for internal fresh commerce. The remaining 50% gets derived for industrial food processing, and this happens when there is a low internal demand for fresh fruit, when there is a low supply of varieties required by the international markets, and usually the fruit that does not comply to the quality standards for fresh consumption gets derived for industrial food processing. This food processing industry works throughout the year to produce clear and cloudy apple juices, apple concentrates, apple pulp, preserved cider, and freeze-dried apple, amongst other apple byproducts. Particularly, apple fruit gets harvested at the end of the summer and can be sold right away for fresh consumption. But since this is a climateric fruit, it can also be stored for 3 months under cold storage to satisfy the demand for internal and external commerce, and also to be derived for industrial food processing. And it can be stored for 3, 6, or up to 9 months under cold storage. Nonetheless, the proportion of fruit that gets derived for fresh commerce and industrial food processing varies along the year with the storage period, and fruit that gets stored for longer periods of times gets destined in a higher proportion for industrial food processing. Apple fruit is susceptible to different fungal diseases in the field and in the post-harvest stage, and it can suffer disease on the outside of the fruit, but also on the inside of the fruit, causing moldy core disease And this disease is believed to start in the field when fungal spores get established on senescent blossoms, and after that gain entry to the center of the fruit via the calcium sinus. When the conditions are favorable, cause the disease. And this disease is of particular relevance when fruit gets destined for industrial food processing, because the controls performed by processing industries usually run this disease undetected. And this is of higher relevance when toxigenic fungal genera are contaminating the center of the fruit. And in particular, species of Alternaria have been reported as main contaminants of apple fruit around the world, causing external lesion and moldy core lesion. And Alternaria species belong to or are toxigenic genus that can produce over 70 secondary metabolites, many of which are considered mycotoxins due to their toxicity. And Alternaria mycotoxins are still considered emerging because it is believed that low evidence on their toxicity and their occurrence data is available. Nonetheless, there are some countries that are thinking or are proposing to legislate some of these Alternaria mycotoxins. Therefore, the general objective of this PhD was to evaluate and provide insights to the evolvement from field to fork of Alternaria populations in apple fruit in Argentina, establishing the risk of exposure to its mycotoxins, and providing a control strategy. And for this, we set up a series of specific objectives, which were to characterize the fungal infection of apple fruit in Argentina from field to process, with main interest on causal agents of moldy core and Alternaria species, to perform a morphological and chemical characterization of the Alternaria populations in apples in Argentina, to identify the most common secondary metabolites produced by this population, to evaluate the production of Alternaria mycotoxins in apple under harvest and post-harvest conditions, to evaluate the effect of the apple concentrate process on the natural contamination levels of 10 Alternaria mycotoxins, to analyze the natural occurrence of free and modified Alternaria mycotoxins in clear and cloudy apple byproducts from the Argentinian market, to characterize the risk from the consumption of these products based on the most relevant Alternaria mycotoxins for the Argentinian population, and to set the basis of a method for a control strategy based on liquid chromatography, high-resolution mass spectrometry to detect apples infected with Alternaria species. So, even though Alternaria species have been reported as frequent contaminants or frequent infectants of apple fruit, this can vary due to climatic and geographic regions. Therefore, the second chapter of this PhD was to characterize the fungal infection of apple fruit. And for this, we selected a total of 240 red delicious variety apples, of which 100 were recently harvested and destined for fresh consumption, and the remaining 100 were stored for 9 months under cold storage. And as well, because pear fruit is cultivated in the same area and it's also sometimes processed together with the apples to obtain apple and pear byproducts, 45 Abatefitel variety pears were also selected. And those were intended for industrial food processing and were stored previously for 3 months under cold storage. The fungal isolation was done in dichlorochloramphenicol malt extract agar. Fungal identification was done according to Pitt and Hawking and Sumton et al. And the type of lesion and the moldy core type, as well as the moldy core grade, were evaluated according to the National Institute of Agricultural Technology of Argentina. When analyzing the results from apples that were destined for fresh consumption, we observed that only 14% of the fruit was undamaged, 52% had external damage only, and 34% had external damage and moldy core. And this corresponded to a total of 86% of fungal infection. When analyzing apple fruit that was stored for 9 months, only 3% of this fruit was undamaged, 48% had external lesion, 2% had external lesion and moldy core, and 49% of this fruit was affected by moldy core disease. And this corresponded to a 51% incidence of moldy core. When analyzing the moldy core type and grade, what we observed was that for a fruit that was recently harvested, all of those fruits were affected by grade 1 of the dry moldy core, while for fruit that was stored for 9 months, we found 39% affected by grade 1 of moldy core disease, 11% by grade 2, and 1% by moldy core grade 4 from the wet type. So not only the incidence of moldy core increased, but also the severity of this disease increased after the storage period. Here we're showing graphs with the percentage of apple fruits that were contaminated with each fungal genus. And on the outside, the outer circle represents the external contamination, and the inner circle, the moldy core infection. So from fruit that was recently harvested, we found 9 different fungal genera contaminating the outside of apple fruit, and 5 different fungal genera contaminating the inside of the fruit. Mainly species of Penicillium were contaminating apple fruit that was recently harvested on the outside, and the second place was also for moldy core disease. And in the second place, Alternaria infection on the outside, on the inside of the fruit was detected, with a 54% incidence of Penicillium species and 41% of infection with Alternaria species. When analyzing the percentage of infection by the different fungal genera of fruit that was destined for industrial food processing, we found species of Penicillium, Alternaria, Cladosporium, and Botrytis infecting apple fruit. And again, Penicillium species were responsible for most of the infection on the outside of the fruit, and Alternaria species was the main fungal infectant isolated from the inside of the fruit. And the storage period changed the proportion of infection from Penicillium and Alternaria. So for fruit that was stored for 9 months, Alternaria was the main fungal genus contaminating or infecting apple fruit. Here we're showing pictures of apple fruit that was destined for industrial food processing with issues of Penicillium species, Alternaria, Cladosporium, and Botrytis species. When analyzing the percentage of pairs destined to industrial food processing with each infected with each fungal genus, we found species of Penicillium, Alternaria, Cladosporium, Pyotricum, Polyptotricum, and Phoma infecting this type of fruits. The external lesion was caused mostly by Penicillium species, and Alternaria species were isolated in low proportion and only from the inside of the fruit. Here we're showing pictures of pear fruit that was destined for industrial food processing with typical lesions of Penicillium, Polyptotricum, Alternaria, and Phoma species. Alternaria species was isolated in low frequencies from this type of crop. Therefore, we focus for the rest of the PhD only with apple fruit. So the conclusions from this chapter were that from a wide biodiversity of fruit that was recently harvested, the storage period seemed to select those toxigenic genus that were better adapted to the cold storage. And Alternaria from a second place gained the first place, and moldy core infection increased its incidence and also the severity of the disease. Nonetheless, not all Alternaria species are toxigenic. Therefore, we decided to perform a morphological and chemical characterization of Alternaria species isolated from apple fruits. And for this, 120 Alternaria strains were morphologically identified according to Siemens, and a subgroup of 74 strains were selected for secondary metabolite profiling. And this was done cultivating each of the isolates in Ries for 14 days at 25 degrees in darkness, and a microextraction using ethyl acetate and 1% formic acid was performed on the colonies. And the detection was made using UPLC high-resolution mass spectrometry that was done in an Agilent Infinity UPLC coupled to UV detector and QTOF mass spectrometer that was used in SE positive and SE negative mode using the aggressive dereplication approach. These experiments were done in collaboration with the Technical University of Denmark. As well, we selected 5 strains that were isolated from different crops for comparison. Briefly, the aggressive dereplication approach consists in running the fungal extracts through the high-resolution mass spectrometer and running each sample against an in-house library that consists of more than 7,500 compounds. And each of those compounds were screened using the retention time, the accurate mass, and the isotope pattern. And as well, we use the different collision energies to fragment each of the compounds. And later, we perform a verification using quant software and the fragment ions and qualifier ions. So when analyzing the results, here we're showing pictures of the different isolates or the different species groups isolated from apple fruit. And those were Alternaria tenuissima species group, Alternaria alternata species group, Alternaria arborescens species group, and Alternaria geissen species group. When analyzing the proportion or the number of isolates that were infecting fruit that was destined for fresh consumption and for industrial food processing, and affecting moldy core disease or causing external lesions, we found species of Alternaria tenuissima, the predominant one, but we also isolate species of Alternaria arborescens and geissen species. The characteristic that they all share in common is that they all belong to Alternaria section Alternaria, which is the one capable of producing mycotoxins. Here we're showing a base peak chromatogram of one of the isolates with some of the identified metabolites. What we found was that a high number of the isolates were able to produce mycotoxins, and the mycotoxins that were produced in higher frequencies were altertoxin 1, tentoxin, tenosonic acid, alternariol and its monomethyl ether, and altertoxin 2. With the production or not production of each of these secondary metabolites, we built a principal component analysis, and here we're showing a loading plot that shows the contribution of each secondary metabolite to this principal component analysis. So strains that have a wider metabolic capacity will appear in quartile 2 and quartile 4. We did not observe any particular difference between the different species group or the type of crops that the isolates were infecting. But when analyzing the type of lesion that they were causing, what we found was that in group 2 was mostly comprised by isolates that could cause moldy core lesion. Therefore, the isolates causing moldy core lesion have a wider metabolic capacity, implying a higher risk for apple byproducts. We also built a heat map based on the semi-quantification on the production of each secondary metabolite. And in this case, we also obtained 2 different clusters, cluster 1 and 2. And in cluster 1 was comprised mostly by was completed by group 2 of the principal components analysis. So not only those isolates infecting moldy core or causing moldy core lesion had a wider metabolic capacity, but also they can produce these secondary metabolites in higher quantities, implying therefore a higher risk of finding Alternaria mycotoxins in the byproducts. So the conclusions from this chapter were that the morphological characterization of the Alternaria species from apple fruit was characterized, with Alternaria tenuissima being the main infectant of apple fruit. A wide in vitro metabolic capacity was proven by these isolates. Nonetheless, this was done under the best conditions for secondary metabolite production. Whether or not these Alternaria species can produce the mycotoxins in apples under the different handling conditions remains to be studied. Therefore, we studied the mycotoxin production of Alternaria strains in apple fruit under retail and storage conditions. For this, we selected 3 Alternaria tenuissima strains that corresponded to group 2 from the principal component analysis, and those were strain 2, 31, and 36. And we inoculated each of those strains in the core and on the exterior of apple fruit separately. And we incubated one group at 25 degrees Celsius for 1 month to simulate retail conditions, and the other group at 4 degrees Celsius for 9 months to simulate storage conditions. We selected 11 mycotoxins for detection and quantification on this experiment, and the extraction and quantification method that we used was one validated in the Center of Excellence in Mycotoxicology and Public Health that consists of a Quetcher's extraction followed by detection and quantification in a UPLC system coupled to tandem mass spectrometry. And that was done on a Waters AKT UPLC CIVO TQS mass spectrometer that was used in the SE negative mode. And for each compound, we selected 2 transitions. One was a quantifier ion and the other one a qualifier ion. And for quantification, matrix match calibration curves and internal standards were used. The 11 mycotoxins that we selected for detection and quantification were Altamaria, its monomethyl ether, Altenuen, tenosonic acid, tentoxin, Altertoxin 1 and 2, and 4 modified forms of the Altamarios. When analyzing the results, we found that tenosonic acid was a mycotoxin that was produced in higher quantities under all the different conditions and therefore was treated separately. When analyzing the other mycotoxins, we found quantifiable levels of AOH, AME, Altenuen, tentoxin, Altertoxin 1 and 2, and AOH3G. And this constitutes as one of the first reports of the in vivo synthesis of Altertoxin 1 and Altertoxin 2, and also the modified form of the Altamaria. We did find that mycotoxin concentration varied with temperature and with inoculation site, and it was highly strain dependent. And as expected, a core infection and incubation at 25 degrees Celsius favor mycotoxin production and accumulation. Storing the fruit under long-term cold storage slowed down the infection of Alternaria in apples and mycotoxin production, but it did not prevent it. Therefore, it's not a good control strategy to prevent the accumulation of toxin compounds produced by Alternaria in apple fruits. So the conclusions from this chapter were that retail conditions, so 25 degrees Celsius and a moldy core infection, was the condition that favored mycotoxin accumulation the most. Nonetheless, we do believe that a consumer receiving a highly infected apple will probably reject it. The long-term cold storage did not prevent mycotoxin accumulation, and this is of high risk because the controls performed by processing industries do not eliminate moldy core apples. Therefore, Altamaria mycotoxins are expected to be present in the different stages of apple byproducts productions. Therefore, we analyzed the fate of Altamaria-free and modified mycotoxins during the apple concentrate production. And for this, we were in contact with an industry from Patagonia that produces apple concentrates, clear and cloudy apple concentrates for internal commerce and export trade. Here we're showing a flow diagram of the production process that starts with the fruit reception. After that, the fruit gets grinded and centrifugated in turbos where skin, seeds, and peduncles are eliminated from the flow line. The resulting juice gets treated with vapor at 100 degrees to extract the aroma, and later on a maceration with enzymes at 55 degrees Celsius occurs. To later decant that juice, and from that we obtain the decanter mats, and a pre-concentration step occurs. If a cloudy product is to be obtained, then further concentration, cooling, and bottling of the cloudy concentrate is done. But if a clear product is to be obtained, then treatment with enzyme and charcoal occurs, and an ultrafiltration to obtain the rejection, and a further concentration, cooling, and bottling of the clear concentrate occurs. We decided to sample 6 different steps for mycotoxin concentration, and those steps are the one here presented with black circles. For this, we selected 5 Red Delicious and 1 Granny Smith processes, of which 4 were clear and 2 were cloudy, and we extracted and quantified the mycotoxins using the same validated methodology as in the previous chapter. When analyzing these results, we found quantifiable levels of AOH, tenosonic acid, AME, tentoxin, and some modified forms of the alternariols along the production process. Notably, the process that was using Granny Smith apples showed much lower mycotoxin concentration, and this has also been reported in other studies that Granny Smith apples are less susceptible to mycotoxin accumulation. For the other mycotoxins and the other processes, we did find that mycotoxin concentration varied along the production process. Therefore, we studied the percentage of variation of each mycotoxin and the influence of each step on the concentration of the mycotoxins. We did found that the out of the process steps reduced mycotoxin concentration, and that the clarification step was key to reduce mycotoxin concentration to non-detectable levels for most of the mycotoxins. Tenosonic acid remained detected even though a clarification step occurred. Therefore, tenosonic acid is expected to be present in clarified apple byproducts. Those processes that did not include a clarification step, the percentage of variation of mycotoxin concentration with regards of the initial concentration of the raw material increased from around 200 times to over 1,000 times. Therefore, the mycotoxin concentration in apple byproducts that are not clarified is expected to be higher. We also found for the first time modified forms of the alternariols as AOH3S and AME3S at different stages of the apple concentrate production, and also in the final product. Therefore, we do recommend to perform more toxicity studies on these modified forms of Altamaria mycotoxins, as well as to include these modified forms in occurrence surveys. Therefore, the conclusions from this chapter were that the clarification step is key to reduce Altamaria mycotoxin, with a particular concern of tenosonic acid in clear products, and that a higher risk is assumed for non-clarified apple byproducts. So the next step that we set for this PhD was to evaluate the natural occurrence of free and modified Altamaria mycotoxins in final apple byproducts. For this, we selected a total of 33 apple juices, of which 15 were cloudy and 18 were clear, and 30 apple purees, of which 20 were infant food and 10 were marmalades. And we selected to quantify and detect 10 different mycotoxins using the same validated methodology as in the previous chapters. From the results of the clear apple juices, we observed quantifiable and detectable levels of AME, tenosonic acid, tentoxin, and some modified forms of the alternariols. When analyzing the cloudy apple juices, we found the same mycotoxins plus AOH. The frequency and the contamination level, so the concentration of each mycotoxin, was higher for non-clarified apple juices, expecting a higher risk from the consumption of these products. When analyzing non-clarified apple byproducts, such as marmalades and infant food, we found levels of AME, tenosonic acid, and tentoxin and AOH3G in the apple marmalades. And in this case, the concentration was even higher than for the cloudy apple juices. For the apple infant food, we found quantifiable levels of AOH, AME, tenosonic acid, and tentoxin. And not only the concentration of mycotoxins in these products was the highest, but also the frequency of finding mycotoxins was the highest. All of the analyzed samples had at least one of these mycotoxins present. And this is of particular relevance because even though infants consume apple byproducts, apple infant food is particularly destined for infants, implying then a higher risk of exposure to these mycotoxins. So the conclusions from this chapter were that Altamaria mycotoxins are widely and broadly distributed in apple byproducts, with a higher risk of finding Alternaria mycotoxins in infant food. But whether or not these levels of mycotoxins are of risk to consumers still needs to be evaluated. So we asked if a processed apple a day really keeps the doctor away, and we perform an exposure assessment and a risk characterization. For this, we selected tenosonic acid, alternariol, and its monomethyl ether for exposure assessment and risk characterization from the consumption of clear and cloudy apple juices and infant food. And for this, we tested two different approaches, a deterministic and a probabilistic one, using the upper and lower bound scenario. The consumption data was taken from the Health Ministry of Argentina, and we selected the age groups of 6 to 23 months old and 2 to 5 years old. The occurrence data was the one presented in this PhD, and the toxicological data that was used was a threshold of toxicological concern for each mycotoxin. So here we're showing the percentage of Argentinian kids consuming these products that are exceeding the TTC values. The deterministic and probabilistic approaches were in line with each other. Nonetheless, the probabilistic approach gives more information on this problematic. Therefore, the results that are presented here correspond to the probabilistic approach. The lower bound scenario corresponds to the best case scenario, and the upper bound scenario corresponds to the worst case scenario. And what we saw that is that from the consumption of clear apple juice, only AME in the worst case scenario seems to be a problem, and a high percentage of kids are exposed to higher levels than the TTC value of this mycotoxin. When analyzing the results from the cloudy apple juices, we found that not only AME is of high risk for the consumers, but also AOH, a high number of, or a high percentage of kids in the lower and upper bound scenario are exceeding the TTC values for these mycotoxins. When analyzing the results obtained from apple infant food, what we found was that from the consumption reported by the Health Ministry and the complete pack consumption, what is recommended by the manufacturers, a high percentage of kids were exposed to higher levels of AOH and AME by the consumption of these products. And over 95% of children from both age groups are exposed to higher levels than the TTC value for AME. Even though tenosonic acid did not have a high percentage of kids exceeding its TTC value from the consumption of these products, it should not be underestimated, because apple byproducts is not the only products that kids consume. And other food commodities in Argentina have been reported as contaminated in high levels with tenosonic acid. Therefore, we do believe that it should not be underestimated. From the number of Argentinian kids that reported to consume these apple byproducts, we calculated the amount of children that are exposed to higher values than the TTC value for the Altamaria mycotoxins, and we think that these numbers should raise concern, and that Alternaria mycotoxins are evaluated for legislation in apple byproducts, especially those that do not include a clarification step, and those that are intended for young children. So the conclusions from this chapter were that an exposure assessment and a risk characterization by the consumption of apple byproducts in Argentina was made, showing that the alternariols are the Alternaria mycotoxins that pose a higher risk from the consumption, especially of non-clarified apple byproducts. And we are recommending that an evaluation on legislation on these mycotoxins is performed. Nonetheless, we do believe that legislation alone does not solve the mycotoxin contamination problem. Therefore, we are proposing an untargeted metabolomics analysis for the detection of Altamaria infected apples. And for this, we selected the samples, the same samples as in chapter 4. So the artificial inoculation of apple fruit under the different conditions. And we performed a different extraction using methanol, water, and acetic acid. And the detection was made using UPLC high resolution mass spectrometry. And this was done in a QT UPLC system coupled to a CNAP G2SI high definition. And this was operated in SC positive and SC negative mode. And the data was analyzed using Progenesis QI. So here we're showing principal component analysis of SC positive and SC negative mode. And we are observing metabolites that come from the apple, metabolites that come from the Alternaria isolates, and the resulting metabolites that come from the interaction. So therefore, we obtain a high number of compounds in both modes, but only selecting those compounds that have a significant contribution to the principal component analysis, we were able to perform a significant reduction and to build this principal component analysis. So here we are showing a big cloud of Alternaria infected apples, and the control samples that did not show any fungal infection were separated from those other samples that were inside this cloud. So here we are proposing the basis of a control method that can be used after the grinding step, and with only taking a small amount of sample with only 2 grams and a very simple extraction and a further high resolution mass spectrometry analysis that consists in a 15-minute run, you could detect Alternaria infected batches and that are contaminated with Alternaria mycotoxins and prevent their processing. So the conclusions from this chapter were that a control method for the detection of Alternaria infected apples was set to prevent mycotoxin accumulation in apple byproducts. So the conclusions from this PhD were that the main fungal infectants of apple fruit from Argentina were identified, showing a high incidence of moldy core infection in apple fruit in Argentina. Long-term cold storage selected those toxigenic fungal genera above the others, and Alternaria was found as the main causal agent of moldy core disease. The incidence and severity of moldy core disease increased during storage, and a low morphological variability was observed within these isolates. Nonetheless, they were all belonging to Alternaria section Alternaria, and a high metabolic and toxigenic capacity of the Alternaria population in apple was observed, showing that isolates from moldy core had a more diverse chemical profile. As well, the mycotoxin production in vivo under retail and long-term cold storage condition was proven, with a higher risk of finding Alternaria mycotoxins in apples that had moldy core disease and that are destined for retail consumption. Long-term cold storage did not prevent the accumulation of Alternaria mycotoxins. The first report on the fate of Alternaria toxins in the apple concentrate production was made, with the first report as well of the presence of AOH3S and AME3S in apple concentrates. The clarification step in the apple concentrate process reduced Alternaria mycotoxins in the final products to non-detectable levels for most of those mycotoxins. As well, the first report of the occurrence of Alternaria mycotoxins and their modified forms in apple byproducts from the Argentinian market was made, with higher levels found in non-clarified products destined to infants. The risk of exposure to Alternaria toxins from consuming apple byproducts was characterized, showing high exposure to the alternariols and higher risk associated to non-clarified products, particularly infant food. A low risk for tenosonic acid was found. Nonetheless, higher concentrations are found in other food commodities. A high-resolution mass spectrometry model was proposed for the detection of contaminated apple batches to prevent their processing and consequent mycotoxin accumulation in apple byproducts. And this model allowed resolution between contaminated and uncontaminated fruit, and it's a promising perspective to reduce the risk associated with apple processed food. The general conclusion of this PhD that was done jointly between Universidad de Buenos Aires and Ghent University allowed to characterize the problem of Alternaria in apple from field to fork, as well as to set the basis for new technologies to tackle the mycotoxin issue. Alternaria mycotoxins are still considered emerging since scarce information about their natural occurrence and toxicity is available. Therefore, the results here presented contribute to widening the knowledge on this topic with perspective for their control and legislation. Finally, I would like to thank both of my research groups and particularly to my supervisors. Thank you very much, Andrea and Virgi. Thank you for all. And of course, thank you very much to Marte and Sara. Thanks to the funding agencies to supporting me along the way. And thanks to my friends and family here from Buenos Aires and my friends and colleagues here from the Department of Organic Chemistry. And of course, thank you very much to all my friends and colleagues from Ghent. If you have any questions, I would gladly answer them.
Muy bien, Agustina. Vamos a dejar ahora al jurado que haga sus preguntas. Well, now it's time of questions. So, Aurélie, I think you may begin.
Great. First of all, we would like to congratulate you on this very, very nice work. I really enjoyed reading your thesis. Thought it was very thorough, very complete, and going beyond detection, but also, thinking about a risk assessment, about a control strategy already. So you really tackled the whole cycle. So that was very much appreciated. Of course, I have a couple of questions for you. And I first would like to start more broad, and then we'll go into the more specific questions for your chapters. In your introduction, you're mentioning that many mycotoxins are able to resist conventional treatments applied in food processing. When we look beyond Alternaria, could you specify for which mycotoxins that it would be an issue that they're surviving the processing phase, and for which ones it wouldn't? And could you also direct them which fungi would be a problem and which ones would not?
Okay, so particularly in apple fruit, or
let's start with apples.
Yeah.
Yes.
Yeah, okay. In apple byproducts, the other mycotoxin that is frequently reported is patchoulin as well, and other studies have been done on the variation on patchoulin levels along the production process, and as well, patchoulin levels are reduced with the clarification step. Nonetheless, detectable levels of patchoulin have been and quantifiable levels as well of patchoulin have been reported here in Argentina in different apple byproducts. So yeah, I think the clarification step would reduce most of the mycotoxins, and patchoulin and Alternaria mycotoxins are the most frequent mycotoxins reported in apple byproducts. Other mycotoxins, I think fumonisins have been, there was one study that reported the presence of fumonisine, but I don't know if they studied the variation along the process or if they could survive the processing the processing stage.
So what about penicillium? Because you also detected it very frequently also in your first chapter. Is there a reason why you focus more on Alternaria and not on this very abundant species?
I'm sorry, can you repeat the question? I cannot hear it properly.
So why not focus your study on penicillium, which was also detected very frequently?
Yes, of course. Penicillium, it's also penicillium is the fungal gene. Penicillium expansum, particularly, is the genes that that it has been reported mostly to contaminate apple fruit. But we were interested in Alternaria species because there are many reports on the incidence of Penicillium expansum in apples, and there are many studies on the occurrence of patchoulin. Therefore, for Alternaria, not many studies have been done. That's why we decided to focus on Alternaria.
Okay. So then about the production of these toxic metabolites, do you have any insights on how this is all regulated and what the production of these mycotoxins depend on, like environmental conditions, plus potentially, you know, regulation mechanisms involved? Do you have some more information on that?
I'm sorry, I cannot hear properly.
Okay, so I'll put my microphone a bit closer.
Yes, yeah, I think that.
Is it better? Okay, yeah. Okay, so let me repeat that. Regarding the production of mycotoxins by Alternaria, could you give me more information how this is regulated in the, in the cells?
By the fungi? Yeah. Yes. Unfortunately, Alternaria, it's a genus that not so much information as, for example, penicillium has been made. There are different pathways that have been proved to be present in Alternaria species, such as acetate pathway that produces the alternariols, altenone, and all of those related compounds. And then some of the other compounds like tenosonic acid and toxin, they're produced via the non-ribosomal peptide pathway, and regulated by that pathway. But yeah, usually for fungal species, those two pathways are the most reported ones. And yes, the metabolites from Alternaria come from those two different pathways. But the production of Alternaria secondary metabolites have been studied in vitro quite a lot. Well, I mean, not a lot, but in our group, we did study that in collaboration, especially with people from the Technical University of Denmark. Yeah, we found that the best conditions for secondary metabolite production were, and this is in vitro, so to cultivate the isolate indrias for 14 days under darkness at 25 degrees Celsius, and that has been showed as the best conditions for secondary metabolite production.
Okay, so the production of these secondary metabolites will very much depend on the environment, right? So of the nutrients that are present on dark versus not dark, all of that. Could it also be a reason why, in the context of Granny Smith apples, for example, you observe less contamination, or does it have nothing to do with that?
Can you just repeat it closer to the microphone, please?
Yes, yes. Okay. Sorry. Is that better? Like this? I'm really holding like my little microphone.
Yes, we have like an audio system here. If not, I will disconnect it and just listen from my computer because there is like an echo, but
yes.
Okay.
So I will repeat. So you mentioned that the production of the mycotoxins depends on the environmental conditions. We found in vitro specific media, specific conditions that are allowing the production of the metabolites. I tried to make the link with the Granny Smith apples, in which you detected, I think, less mycotoxins, but also less fungi. Is there a link with the environment there, or what's your thought on that?
Yeah, there are different theories on why fungal infection and mycotoxin production on apple fruit, Granny Smith apple fruit, is lower. One of those reasons is due to the acidity of Granny Smith apple. They're more acidic. Therefore, it is believed that mycotoxins, or actually fungal infection, is less frequent on that that variety of apples. And particularly with moldy core disease, red delicious fruit have an open sinus with that facilitates the infection by Altamaria because it can enter the center of the fruit more easily, while Granny Smith apple have has a closed sinus. Therefore, the infection is much more difficult for Alternaria. And there is another thing also that maybe, but this has not been studied. It's a theory only, that we did find levels of AME3S, I think it was, so a modified form of Alternaria mycotoxins in Granny Smith apples, and those metabolites are believed to be detoxification mechanisms of the plant. So probably there are some very complex mechanisms that the fruit has to prevent infection and mycotoxin accumulation.
Okay. Very good. My next question, which is a question I had throughout your whole thesis. So you found the toxins. They can be associated, of course, with the wounds of the apple. They can be in the core, the moldy core. But if the fungus produces these toxins, will they be able to diffuse throughout the meat of the apple, or will they stay very localized?
Well, there are studies that show, but most of these mycotoxins are soluble, and the apple in particular has a high amount of water. Therefore, the mycotoxins are soluble and can diffuse in the apple. Of course, a higher mycotoxin concentration is expected in the wound itself, but the diffusion, it's also expected. There are some studies, very recent studies that study that, and yes, in closer to the lesion, the mycotoxin concentration is higher, but on the other parts of the fruit, the mycotoxin concentration was also found. But this, of course, is of relevance, but when fruit is derived to byproducts, it's grinded all together, so it doesn't matter whether or not the diffusion of mycotoxins. But yes, it can diffuse around the apple, but yeah, in the lesion, the concentration is higher.
So for fresh consumption, once you remove indeed the wounded area, we should be safe. Or safer, yeah. Let's say that way. Yeah. Okay.
Yeah, that is a question that everyone has. Yes, it's safer. It's safer to remove that area and consume the rest. But yes, it can diffuse. It can diffuse. Yeah.
Exactly. Yeah, it's important, right? Because since reading your thesis, every time I have an apple with a moldy core, I'm like, should I throw it away or not? So, but yeah, so probably yes, but yeah, okay. Yes. All right. So moving to, I'm already moving through all the chapters. So of course, if any of the other jury members have questions, feel free to interrupt them. So for your chapter 4, I would like to take you to table 4.5, that is, where you have like all the different metabolites. Let's see, it's on page 109 in your thesis, if you have the thesis in your bag.
I can open the thesis if you like.
Yeah, sure. It might be easier for you to locate.
I don't think I copy that table here.
So let me know when you have it.
Yes.
If you want, I can already ask the question because maybe you will know by heart.
Okay, yes, you can. Maybe I don't.
Okay, so in your table, you actually have the inoculation site, you have exterior, you have core. There are always 3 like replicates there. Is that from the same apple or from different apples? Like, how should I see this? What are these replicates exactly?
They are all from different apples. So each strain here. Are you seeing my screen or not? No, it's showing here.
No, you have changed.
I have to share it again.
Yeah.
Okay.
So you probably have to unshare first.
Yeah.
Exactly. Perfect.
It's okay. Yeah. Okay. Great.
Okay,
Okay, so yes, each of these correspond to a different apple.
Okay, all right. So for some of those values, you actually, and for some of the mycotoxins, you actually see quite some variability. For example, with the 10TN, you can see,
yes,
you know, those values are very different, but it's for pretty much all of them. So is that something that you would expect, and yeah, is it really depending on the amount of fungi, or is it the methodology which should still be optimized a bit more, or what are your thoughts on that?
Yeah, the amount of fungi was the same for all of the apples, because we did solutions or suspensions of the fungi of the different isolates that were quantified, and then we inoculate them with a calibrated loop. So the amount of fungi that was inoculated was the same, but these different mycotoxin concentrations are expected because fungi are living organisms, and even though they were all inoculated under the same conditions, they can produce mycotoxin concentration in different amounts. That's why we did, for each strain, we did it in for a triplicate for each strain under each condition, because these variations were expected.
Okay, because look at only the TEA, like the first three values, you have like go from 500 to like 20,000 microgram per kilo. So I can also imagine that the downstream toxicity or potential toxicity can be very different from apple to apple. Then
yes, it can, and that's why we did the triplicates for this, because we were expecting different mycotoxin concentrations.
So here I was unable to find an uninoculated control. Did you include it to see what the background levels were?
Yes. For this, yeah, I did not include it in the table because mycotoxin contamination on the controls was non-detected. But we did use those samples as blanks to build the matrix match calibration curve. So when building those curves, we also there is a blank one, or blank sample that we use as control, as a blank sample, as the 0 value for the calibration curve, and that has no mycotoxin contamination. Yeah, no concentration of mycotoxins. It's not included here, but controls were 0. Yeah.
Okay, should I continue, Alicia?
Sorry?
I was just asking, should I continue? Yes, so feel free to interrupt anyone if you would like me to. Yeah, so I'll just continue as long as no one interrupts me. I'll just continue asking my questions. So
if you have more questions, you may continue. No,
okay,
no problem.
I definitely have more questions. So.
I have some questions related to the same table, but I will wait my turn.
No, go ahead, Marcelo. I think it's a good idea for you.
No. Because it's related with other previous question that I have to ask. Okay. So I prefer to wait.
Okay, perfect. So Agustina, so you mentioned that you wanted to perform pathogenicity tests also for this chapter, but due to, we all know why and the reasons, you weren't able to do it. What would have this been, what did this imply, these pathogenicity tests? Can you give me more information?
Yeah, the pathogenicity test is to evaluate the proportion of infection, to say it in some way, of each of the strains. It's something commonly done with a plant pathology, and it consists on measuring the lesion throughout the different inoculation period, and that will give you an idea on how pathogenic the isolate is. So sometimes it can cause only a small lesion or a bigger lesion, and that can vary through the time. You can calculate the speed of infection, but it was just to give more information on the infection of Alternaria species in apples. But yeah, you have to take daily measures, or yeah, sometimes maybe once every 2 days or 3 days, but yeah, I could not access the faculty during COVID, and therefore I could not perform that.
Okay, all right. Good. So moving on to the fifth chapter of your thesis. I think first a results question. So on page 131, you have like the graphs in which you see the concentration of the mycotoxins going up and down with the different procedures.
Yes. 131. Okay, yes, here.
Yeah, exactly, that's it. So there I was wondering, so for some of the metabolites you see it's going up, for others not really, there's like a big difference sometimes. I would have expected like even if you would have an increase due to, for example, concentration or another procedure, it would be very similar for all of them, but that's not the case. Like look, for example, at the 10, step 6, like it goes quite up there. Well, that's what I mean indeed. Compared to like the other toxin right above, the increase is much lower, and compared to the AME, it's not even increasing. So how can you explain those differences between the metabolites?
There is a difference if you look at AOH and AME, that they have a similar chemical structure. They vary quite similarly, but the other mycotoxins that have a different chemical structure, they vary very differently. And that can be due to their solubility. And for example, tenosonic acid, due to its acidity, we show that it also varied because of that. And for example, yeah, the step 6 is the rejection, so the last out of the process step. And AOH and AME were not found there, but tentoxin and tenosonic acid, they were found there. But if you check the structures of the molecules, tentoxin is quite a big molecule, and tenosonic acid, it's an acidic molecule. Therefore, we believe that it's due to that that we observe the different variations.
Okay. And so in general, the culturing process of apples, are no fungicides involved?
Yes, I did not show it in the presentation, but in this chapter it's mentioned that we did study processes that were made with organic apples and processes that were made with conventional cultivated apples. So with the application of fungicides, and only tenosonic acid was higher for the organic process. But the problem with Alternaria and with the fungicides is that Alternaria causes mainly moldy core, and the incidence increase during the storage period. And if you want to prevent moldy core, the application of fungicides needs to be made in a particular period of time, and it can be dependent on climatic conditions and other conditions. Therefore, if you, let's say, spray fungicides for Penicillium expansum that causes the external lesion, it will actually favor Alternaria infection, because once it is inside the fruit, it is protected against fungicides, and it eliminates the other competitors. Therefore, it can grow more easily. So yeah, the application of fungicides, it's quite common here in Argentina, but it does not solve the Alternaria problem.
Okay. Good. So I have 2 more questions to also allow sufficient time for the other jury members. So one question is about the choice to use an untargeted approach for the future control strategy, for the detection of the mycotoxin. Why did you choose an untargeted approach and detecting all of these more than 10,000 compounds, and why not focus on like a very targeted approach, which you could very nicely quantify select compounds?
Well, actually, it was done this way because the untargeted method, it's very easy. For quantification, you need to perform a lot of different analyses. Like you have to have a matrix match calibration curve. You need to have the standards. You need to know which mycotoxins could be present and in higher amounts. With the untargeted analysis, the extraction is very easy. And the detection as well. It's just 15-minute run. You don't need any standards. So it's quite easy. Once you have the method set for your kind of apples and your crop and the Alternaria population affecting the kind of apples that you process, then it's much easier, and you don't need to identify each compound. So that is why we're proposing this. Yes, of course, you can quantify it and see if it's contaminated or not, but you need to do more things to obtain that result. This method, it's very straightforward, and it's very easily performed, and you don't need to identify anything. I did not identify any compound there.
Okay. And then a final question, the other one I'll keep going. So it's about the effects on the patient or the future patients. So can you give more information on once you take up these mycotoxins, where in the human body do they end up, and how could they potentially cause disease, cause cancer? What's known about that already?
In the body, you mean?
Mm-hmm.
Oh, actually, not many studies about that have been made for other most popular mycotoxins. For Altamaria mycotoxins, currently there is one PhD student in the Center of Excellence in Mycotoxicology and Public Health that is studying that. So the biotransformation of Alternaria mycotoxins in the body. But currently there is not a lot of information on the mechanism of their toxicity, unfortunately, but more studies are being done for that. But yeah,
we think the evidence between the link of mycotoxin accumulation or exposure and cancer at this point, is the evidence strong enough to, for example, really based on your data, suggest new guidelines or really applied knowledge that you have?
Yeah, for other mycotoxins, for sure. For Alternaria mycotoxins, that it's currently being studied. We do have the threshold of toxicological concern, but that is like a safe limit that, below that quantity of mycotoxin ingestion per day by body weight, by kilogram of body weight, that below that limit, it is safe, but above that limit, we actually don't know what will happen. We believe that toxicity is expected, but of course, the long-term exposure to mycotoxins is the biggest problem. Only tenosonic acid exerts acute toxicity in very high quantities. The other mycotoxins are cumulative ones, and the worst case is that these mycotoxins are widely distributed amongst other products as well. Therefore, the total intake, it's not only the one showed here, but it's much higher. What happens inside the body, it's being studied at the moment to possibly relate these mycotoxins with cancer or other diseases. Some studies have been made relating this. For example, tenosonic acid has been related to onilai, which is a disease in China, and it has been related because of the high consumption, I think, of rice. So, but yeah, more studies need to be made for that.
It's too early to really already propose to the authorities that the Alternaria mycotoxins should be monitored more closely in the food processing system? Or are we there yet? What do you think?
I think we're getting there, and probably, yes, I would not say it's not a problem, let's not regulate this or let's not study it further. For sure, we do need more studies, but I would at least recommend safe limits for the mycotoxins.
Okay, great, thank you very much.
Thank you.
Okay, so Marcelo, it's your turn.
Okay. Hello, Agustina, how are you?
Very good. Hello, Chelo.
First of all, I want to congratulate for your work. As you know, this type of PhD works, I appreciate this approach because it's not a classical approach to study deeply a specific topic, but you follow the agri-food chain and use different approach to analyze the problem, and you conclude about the risk of public health. Normally, the PhD students don't, it's like the mycotoxin is a mycotoxin, the problem is a mycotoxin itself, and not at the end, the problem is a public health problem. And you approach the huge problems, and so appreciate this idea. As you know, my research area is not the apple mycotoxin so I concentrate my question in the statistical approach, the observational designs, and the quantitative risk assessment. So I will be the bad guy in this in this committee. Huh? I will follow your structure, chapter by chapter. In chapter 2, you took 240 samples, apple samples. Could you explain me more about where the origin of these apple samples, which how many farms were included in this sample?
Well, for the fresh consumption apples, we were in contact with people from the Mercado Central of Buenos Aires, and they were the ones that provided the samples. Unfortunately, we do not know how many different farms or orchards were included in that. But for the fruit that was stored for 9 months, the samples were provided by the same company that produces the concentrate, and they were all from one orchard, and they were stored and they were taken from one process. Just before processing them, a subsample was taken from that, and they were all stored together as well.
Okay. Do you think that this is a limitation of your study, or it's okay?
Yes, of course. Of course, it will be more, or it will give more information to know the exact orchard that the apples were harvested at, and all of the conditions, etc. But yes, sometimes you have the samples that you have, and yeah, that is the case.
Okay, but in your conclusions, you said, I am reading your PhD thesis, the main fungal infectants of apple fruits from the Alto Valle of Rio Negro region. Do you consider that your observational design could support this conclusion, taking in consideration the limitation that you took samples that you can, not as you want?
Yes. The case that we would have sampled only one orchard, then that conclusion will be wrong probably. But
no wrong, maybe not wrong,
or not complete, or not accurate. But I think that given the fact that different orchards and actually the fruit that it's destined for fresh commerce here in Buenos Aires, we sample many different orchards, then that conclusion would be more accurate in that case.
Yeah. Maybe if you want to estimate the prevalence of mycotoxin or fungal contamination, you have to design a completely different
Yes. Yeah.
Seven. But I know that the distance is not appropriate to conduct accurate observational design. But you have to take in mind that your conclusion have to be related with the sample's origin. No? Your sampling design have to support your conclusion. If your design is restricted, you have to be more cautious. It's maybe related to the other region, maybe it's too much. Yeah, that's my only consideration. Okay. Yeah. I will be back to the table in chapter 4 related with the question, the previous Aurelie's question. In this experimental design, you use 3 replicates. Yeah. And obviously, as you said, this is biology, and obviously if you put the exact same concentration amounts, but biology is biology, life is life, and some samples have a high level of metabolites and other a lower level. So it's acceptable. Yes, really acceptable. But to analyze statistically these results, you use multifactorial ANOVA. Yeah. Do you think that this statistical approach is appropriate for this type of variable and for this distribution, very biased distribution?
Yes, maybe a different statistical approach could have been used.
For example?
Well, maybe to look for the distribution of the concentration for each mycotoxin. Yeah, maybe we have used at risk. Yeah, but you do know that the software is paid one, and I could use it only for a limited time. But yes, maybe a different statistical approach could have been used for this as well.
Yeah, because for example, for tenosonic acid, you set a typical large residue in homocysteicity, and that's the reason why you didn't analyze this mycotoxin.
Yeah, we had to treat it separately. Yes, because the amount was much higher.
Yes, but if you use, I could recommend you for this type of data, you can use generalized linear models, because with this type of models, you can put a different distribution with different shapes, bias, not bias, homocysteicity, it's okay or not, no matter. You can put all type of variable in this type of model, analyzing the shape of distribution, and choose the tool, the more appropriate tool for this type of distribution. For future, if you want to use, the generalized linear models could be very useful for this type of experimental design, because obviously I think that analyze this type of metabolite is very expensive, and the experimental design is very hard. So you can use only 3 replicates, and it's reasonable. But this type of models could be useful for you.
Okay, yes, I took note of that to further analyze it.
Finally, obviously, I have 2 or 3 questions about the quantitative risk assessment. I really appreciate that one of my students have conducted a quantitative risk assessment. You are brave. Yeah, I appreciate that. But
I appreciate you teaching me.
I have two questions. Why did you use the lower and upper bound scenarios? Why you only use these two scenarios?
Well, yeah, we could have used a middle bound scenario as well. But yeah, that was another option. But I think it was maybe more in line with the deterministic approach, in which you use the mean value. But usually the lower and upper bound scenarios are used when there is a lot of less left sensor data, which was the case for some of the food commodities, and that would solve the left sensor data issue.
Yeah, but when I saw your tables about the proportion of people estimated who ate a higher level of mycotoxin, I say, oh my God, what happened with this? Please, somebody who could take into consideration our babies. Yeah. What is the problem with this approach?
Sorry?
What is the problem with this approach to use only the lower and upper bound?
Yes, that you're using the best case scenario in which like the non-detectables are 0 for mycotoxin concentration, and the worst case scenario it's where all of the samples have actually the non-detected or the ones that were, because with the lower and upper bound scenario, what you do is you work with those samples that are between LOD and LOQ, which I had a few of those. But yeah, the worst case scenario, it's like, okay, what if if we don't control the Alternaria issue, and if we if all the samples, or not all the samples, but for example, but for AME, for example, for infant food, all of the samples were positive for AME, and I think that was the case. Therefore, the upper and lower bound scenario were the same, and in both cases had more than 95% of the children. And in that case, I did not replace any contamination value. I think maybe 1 or 2 were between LOD and LOQ, but all of the samples had that. But yes, of course. And I think we do want to raise awareness that Alternaria in apple is a problem, and that authorities should look further to it. But yeah, it is an overestimate.
I'm okay with your conclusion. Yes, maybe this is right. The problem is that you need the probability associated with this event, with this scenario. If a meteorite fall over my head, I have 100% of chance to die. Yeah, it's okay. But what is the probability associated with this event? Okay, it's really infrequent. That's the problem with lower and upper bound. And you use extremely power software at risk, and you can use all the distribution, and you give a more realistic scenario. You can consider all the distribution, and you can show the complete scenarios, and not only 3 or especially 2.
Yes, huh? Yes, of course. From the distribution, I have the tables and everything. It was not shown in the PhD because it was quite rather long. But yeah, I have all the distribution with all the values.
Right, that's right. The last question for me. This mycotoxin have short-term toxicity or chronic toxicity?
They have chronic toxicity, so they accumulate in the body, and the problems are not acute, but they are cumulative, and they will, or it is believed that they will affect it in the long run, in the long periods.
Okay. So the toxicity is associated with the frequency of exposure.
Yes.
Okay. How many exposures have to expose a child during a year, for example, to be problematic? How much?
Well, I don't know. The only toxicity data we have, it's per day. We don't know it yet. If, let's say, if you are exposed to these mycotoxins for a year or a month or a week, or we don't have that information. What is preoccupying is that a recent study that analyzed breast milk, it was also contaminated with Altamaria mycotoxins, especially AME, I think it was. And so the babies are exposed to it every day. And the main problem with the Alternarials is their genotoxicity, but also their estrogenic potential. Therefore, yes, I don't know if the toxic effects will exert in how long, but I think it's for children that have low body weight and their immune system is not fully developed. I think it's quite problematic.
My question is related with your estimation about the number of children who will be exposed to high level of this mycotoxin. But you suppose that this number of child will consume for a long time this type of products.
Yes, and not these only products, but other products. For example, for other like infant formula or infant cereal-based products for infants, they are also contaminated with Altamaria mycotoxins. So I do believe that a more comprehensive risk assessment should be done, including other food commodities and updating also the consumption. As you know, the data from the last ENIS is not available yet, but I think also these products like the pouches for fresh apple puree or apple infant food, that they suggest to eat the whole thing, and I think we need more occurrence data, more a more comprehensive study, including other food commodities. That is also good.
Exactly, like a total diet exposure. Yeah, but in your total diet is a hard work, so you can do it in another life if you want.
Yes, of course.
But in your work, you can put together the different food matrices: apple juice, infant formula. I don't remember the other matrix.
Yes.
You can put them together and estimate the exposure like a partial total formula.
Totally. The problem is that in Argentina, there are not many occurrence data in Altamaria mycotoxins. I think our group and another one, or maybe two others, are working on this, but there is not much information on that. I did do a literature research looking for that and looking for other occurrence data on apple byproducts, and there was nothing on that. So that's why only this study was included.
Okay, excellent. That's all for me. Thank you very much.
Thank you.
Okay, so now Lydia's turn.
Hello, are you listening to me?
Yes.
It's
okay.
Okay, well, first of all, I like to congratulate you and your two supervisors for this fine work. I really like it. I think this work is a contribution from both the theoretical point of view and also from the practical point of view. You have studied Alternaria species, and they are mycotoxins from the field to the table in any steps, and also in processing foods, following step by step the processing. It's a very complete and deep work done with very nice and new techniques. I think is really excellent. I have some comments. I enjoyed very much reading this thesis for some reason. I'd like you to comment on something I'm going to tell you. I have a question also related to sampling, as Marcelo did. In figure 2.2, you show the percentage of apples contaminated. And when I saw this number, I was actually scared because they are too high, actually. My question is the selection random? I mean, does this number represent which is happening in apples in Argentina?
Yes, the selection was made randomly, yeah, those are the numbers. The selection was random, but well, for apples destined for industrial food processing, they were highly contaminated, and it was very rare to find one that did not have any fungal lesion on the outside or on the inside. It was very rare. For the apples for fresh consumption, the selection was also made randomly, and I do believe that there are different factors that were influencing the external infection of apple fruit. For example, the handling, and as well, the apples are very susceptible to bruises and punctures, and fungal spores then get established there. And maybe the lesion was very incident, or it was very small, but I could isolate it, and maybe the lesion was not super huge, it was only a small one, but yeah, the selection was one.
And did you find contamination in fruit that has intact skin?
I don't think so. No, if it had, I mean, on the inside, yes. On the outside, most of the contamination was, it had at least a small lesion, maybe caused by the fungi, or maybe it was previously there and then the fungi gained entry. Penicillium expansum, for example, there has to be a lesion before. But yeah, so on the inside of the fruit, maybe on the outside, the fruit appeared beautiful, but on the inside, it was contaminated. And that is one of the problems with moldy core, that maybe on the outside, the fruit looks very good, but on the inside, it's not so good.
This is a very original result, because people always believe that if the fruit is okay, the skin is intact, everything is okay. But if you have the core contaminated, it's not.
Yeah. Totally not. Yes.
So in chapter 4, you wrote something I think is a very good contribution from the practical point of view. You said long-term storage at 4 degrees centigrade did not prevent accumulation of mycotoxins. And this is a so common practice in industry. So that does mean it is not as successful as a producer believes it is.
Yes. Storing the fruit did not prevent mycotoxin accumulation. It is quite interesting because most of the processing industries here, or the pack houses, they only perform storage under cold storage. But some other studies are researching on the impact that modified atmosphere had, for example. Maybe that is a promising control strategy for storing the fruits. But yeah, only long-term cold storage did not prevent the mycotoxin accumulation.
Okay, and I also want to point out two things I think are really important. In chapter 5, you say that process-free is organic and is highly contaminated with tenosonic acid. So many consumers believe that if something is organic, it's safe. And this for me is a revolutionary idea.
Yes.
Again, this misconcept. I mean, technology is not bad. Sometimes it's good. Process the food doesn't mean it's bad. It's really,
yes, it depends. It depends on what side you're looking at it from. If it's from the mycotoxin accumulation point of view, then yeah, probably it's not the best. But if you look at it from the pesticide point of view, then yeah, organic crops are better from that point of view. But I don't think there is a comprehensive study that can evaluate all the different toxicity aspects of the compounds that are there. And I don't know the exact toxicity compared of the pesticides or fungicides against the toxicity of mycotoxins. If you put it in a way, I don't know which one is best or which one is the worst.
Oh,
So,
yeah, that's right. That means it's a complex situation. It's not like linear, organic good.
yeah.
That's very interesting for me, very interesting. And another thing I really love was you say in page 139, on the contrary, cloudy process show much higher final levels of the food for mycotoxins. And I love this phrase because people believe that natural means safe and natural food means live forever. And that's not true because the most strongest poisons are from natural origin. So
yes, yes, in some cases, but again, you have to weigh a lot of different factors. Like for example, clear apple juice has a higher glycemic impact because it's mostly sugars, has no fiber, and then it's consumption of sugar. Then you will have, I don't know, non-alcoholic fatty liver, which is a different disease. But if you consume cloudy products, you are consuming fiber and other polyphenols and other compounds that are healthy for you. But then, yes, you have mycotoxins and probably other pesticides and other things. So yes, it's a very complicated balance.
That's right. I think this approach is really a contribution because there is a general idea that natural means safe. So it's not like this, not always.
Yes. Yes, not always. Yeah, that's the case.
So thank you for inviting me for this. It was a pleasure to read this manuscript.
Thank you very much, and thank you very much also to Aurelia and Marcelo. Thank you very much for evaluating this PhD that I know has had some complications, and it's being a joint PhD, it's more complicated. Also, thanks to Dr. Rodriguez and Dr. Couto for taking, and also the secretaries here for taking the special time for doing this. I do appreciate it.
It was a pleasure.
Me too.
Thank you very much.
Bueno, now we are passing. Lydia will be the
host.
The host, and we will stay out of the video, and only the jury stays in order to